So this quadratic is solved differently than a linear would be. Whereas we'd normally for a linear put all the x's to one side and all the constants to the other, that's not the way we solve a quadratic. First step in a quadratic is to get everything on one side so that your expression, your equation is set equal to 0. And then the second idea is that adding or subtracting numbers together to make zero, there's just too many possibilities. So we don't want to do it that way. What we want to do is express it as a product of two things. Because if I have two things multiplied together equaling 0, one of those things must be 0. In order to take this expression and turn it into this, we have to think a little bit about how we multiply things like that. Like, let's say I had x plus 2 and x minus 5. And then we're multiplying them together. Please listen, guys. X times x gives me x squared. 2 times negative 5 gives me negative 10, but that's not all of it, is it? When we do this distributive property, we have to do the outer terms like minus 5x and the inner terms plus 2x. And in the end, these two things get muddled together to make that. So the strategy or the challenge in what we're doing now is we have to take this middle term and break it up appropriately so that it splits out. And that's what we're struggling with here. This negative 3 could be a negative 4 and a positive 1. Could be a negative 5 and a positive 2. Could be a negative 6 and a positive 3. Could be a negative 103 and a positive 100. So we have to figure out what that is. We have a tool for that. We call it the diamond, which is where we take this constant in the end, negative 108, and this works anytime we have a lead coefficient of 1. And then we take the coefficient of our x term and put it down here. We're looking for what two numbers multiply to make negative 108, while at the same time adding to make a negative 3. Now I could come at this either direction, but there are infinite numbers that that add together to make negative 3. Right? I just listed off a few of them, negative 4 and positive 1, negative 5, positive 2, negative 6, positive 3. There's not a limitation on those. But if I know they're going to be integers, and they are, and they multiply to make 108, that's a shorter list. So I'm going to start thinking about what numbers multiply to make 108. Well, it could be 108 and 1. It could be 54 and 2. It could be 336. 36 and 3. How do I know which ones are right, though? If I want this number to these two numbers to multiply to make a negative 108, what has to be true about one of these? One of them has to be negative. And if a number is negative and the other one's positive, when I add them together, it's really like subtraction, isn't it? So if the numbers were 36 and 3, when I add and subtract, it's going to end up being not a negative 3. It could be a 33 or a negative 33. They're too far apart. This is 107 apart. This is 52 apart. This is 33 apart. They're too far apart. I need bigger numbers here. I could try 4, but that's not going to be far enough. So I'm going to jump a little bit. I'm going to go with like 6. 6 goes into this 10 and 48, so 18 times. And 6 and 18 are 12 apart. That's still not the 3 I want. I need to get closer. Maybe I'll try 9. 9 goes in 12 times. There we go. 9 and 12 are 3 numbers apart. So if I were to add one of these being a negative, the bigger one, negative 12 and positive 9 makes a negative 3. So I'm going to put those numbers down here. Because this is the simpler version where the lead coefficient is just 1, I know that my lead terms here both multiply to make x squared, therefore they're just x. And what I did here was enough to fill in here. That's my factored form of this expression. I'm not done because I still have to solve for x, but that gets me the critical part. Now, if either x minus 12 equals 0 or x plus 9 equals 0, so that when they multiply together, they make 0. It means either x minus 12 equals 0, so x equals 12, or x plus 9 equals 0, so x equals negative 9. In the world of algebra, both of those solutions are valid. But today we're going to be working with geometry where x is going to reflect the length of a segment. And because of that, does it make sense that x would be a negative 9? No, you can't have a negative length. So although the algebra says there's two answers here, we're going to end up crossing one out and saying that because of the geometry, we're only keeping the positive answer. All right. 5, this has always been my jam. I can factor like nobody's business. 3, I think I have some confidence now. I could probably do this again. 1, this is a skill that I still need to fix. Okay. All right, you'll have some chances today. Let's take a look at the notes. Actually, before we do notes, I guess I better prove you the first theorem. So what we're looking at today is when I have chords and secants crossing through a circle to meet, we've talked about their angles and what angles they formed. Today, we're going to be talking about the lengths of the segments formed. So for example, if I label this A, B, C, D, those 4 lengths are all formed by these two chords intersecting. And there's a relationship among them. To see that relationship, what I'm going to do is I'm going to connect these ends and connect these ends, making two what's? Triangles. We love triangles because we can prove them as congruent or similar or in some other way interesting. Are these two triangles congruent? Said very firmly, they sure don't look congruent. Do we have any information about them? Like, we know these are vertical angles, right? So that part's easy. They do have an angle pair in common. Do they have anything else in common? What about those two angles? Why?
Chose those two.
Yeah, they're inscribed angles that share the same arc. They're called overlapping inscribed angles. So since this one would be half of this yellow arc, and this one would also be half of this yellow arc, those two angles are the same. So now I've got 2 angles in the triangle, congruent to 2 angles in the other triangle. What does that let me say about these 2 triangles? They're congruent? I don't think that's one of our theorems to prove triangles are congruent, is it?
It's a stretch.
It is a stretch. We had like side, 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 and side, angle, side, and angle, side, angle, and RHL. But I don't think AA proved triangles congruent, did it? It proves they're what? Yes. It proves they're similar. So once these 2 triangles are similar, I can then say that corresponding parts are proportional. That's what similar triangles give us, which then lets me cross multiply to say that A times B equals C times D. So what that means for us is that if I have a circle and I tell you that this is 6 and this is 4, what do those two multiply to make? 24. If I tell you that this is X and this is 8, what does X have to be so that it, when multiplied times the 8, also makes 24? 3. So X would be equal 3. That's the relationship we're going to discover. Let's put that into our notes. So when this is the setup where you've got an awful printing, and I'm very sorry for that, when you've got A and B as part of the same chord, it's A times B equals the other two partial chords multiplied together, C times D. What would that look like? Well, let's take a look at number 1. If X and 10 are part of the same chord, I can say 10 times X equals what?
14 times 15.
Yeah, 14 times 15. So 10X equals 210, so X equals 21. We should be able to ratchet things up a little bit. We're going to look at problem number 2 now. What's my setup?
Find 6 equals 4 minus 5x minus 1.
Very nice. So 36, and I'll distribute here, equals 20x minus 4. Add 4. Divide by 20. Am I done?
I know.
Good. Why not?
Find BD.
Yeah. The question ratchets it up a little. BD is 4 plus 5 times whatever we found as X. Well, we just found X is 2. So 4 plus 10 minus 1, 14 minus 1 is equal to 13. That's my answer. Would you please do number 3 yourselves now? Go. Please take a look at the answer here. See if you have any questions or concerns. How's this feel? 5, this feels very straightforward. I'm going to be able to do this one. 3, I think I can do it with the notes. 1, I'm going to be in trouble. Okay, good. So I want to take you to prove the next one, which actually applies in 3 different venues. This is what happens when we have a circle, but now the point of intersection is outside the circle. So it's not 2 chords meeting. Now it's going to be 2 secants, or as it'll turn out, 2 tangents also, or one of each. If I label this segment that's formed and this segment and this segment and this segment, I want to find a relationship among them. As is so often the case, triangles get us there. So I'm going to draw that little line in, creating this triangle. And then I'm going to draw that one in, creating this triangle. What's true about these 2 triangles? What should you be looking for to decide if anything's true about these 2 triangles? Congruent angles, congruent sides. Do you see any angles that are congruent? Which ones? One, 3, 2. Oh, I see. You're saying angle 3. Yeah, I wasn't putting letters in there. So angle 3 is shared by both of them. It's reflexive. So that's going to be congruent, right? What about angle 1 and 2? Good. Excellent. They're congruent because they're that overlapping inscribed angle thing again. They're inscribed angles that meet the same arc, so they're also congruent. So if these two triangles are showing two angle pairs that are congruent, then these two triangles are what? Similar again. And if they're similar, we can say that corresponding parts are congruent. So what I'm going to set up is that the yellow triangle is to the green triangle, right? And I'm going to choose some corresponding parts. So in the yellow triangle, I'm going to choose the long side, A plus B. And that means in the green triangle, I also have to choose the long side, C plus D. And now in the yellow triangle, I'll choose the short side. And then in the green triangle, I'll choose its short side. And again, I'll cross multiply. Now, I hate the idea of giving you guys this formula. There's 6 variables in it. Well, not really, there's 4. But depending on where you put them, it messes everything up. And if you happen to label your triangle A, B, C, D, then this doesn't work any longer. So I have a different way I like to think about this. I'll give you that format of it. Here in the notes, we can see that what we're saying is that A plus B times A is C plus D times C. That's the formula, but it only works if you've got the letters just that way. So I like to think about it differently. A plus B is the entire top measurable stuff, right? This part goes out forever. This part goes out forever. So those aren't measurable. So A plus B is what I call the whole. Versus A, which is just the measurable part on the outside. So whole times outside equals, what do we have for the other one? Same thing. Whole times outside. And by thinking about it that way, we can apply it without having to consider which letters are where and matching it up and getting brain cramps trying to do that. In fact, it works so pretty that it works in this one as well. So what's the whole of this bottom one? Good, but we were adding them, right? B plus C. And what's the outside? B of the same segment equals, now here's where it gets weird. What's the whole of this top one? Yep. And what's the outside? A, so it's squared. In fact, this also works for the one we did last class. If I take a circle and 2 tangents, and I label this A and this B, I could call it whole times outside, or A squared equals whole times outside, or B squared, but that just simplifies to A equals B, which is the way we learned it. Not C, A equals B. So whole times outside equals whole times outside works for all 3 of these. If you just need to memorize or pull out of your memory one theorem, that's the one. So let's go down to number 5 and apply that. So what would be the whole length of this chord or secant? Almost. Good, exactly. You add them together, so 9 plus x, and then times the outside is 9 equals what? Eight plus 19 times the outside of 8. Whole times outside equals whole times outside. Then we distribute 81 plus 9x. We could distribute here, or we could clean up in the parentheses. 27 times 8. So 81 plus 9x equals 160, and 56 is 216. Subtract the 81. 9x equals 135. Divide by 9. X equals 15. I always find this one is hard to set up correctly. So let's do one together, and then I've got several for you guys to work on as practice. Everybody look at this one and try to set it up. Can I get a volunteer who hasn't been contributing yet today to please tell me how we should set this up?
Hey, I'm just wondering, how did you get 27 on the original one?
I took the 8 and the 19 inside the parentheses and just combined them. Yes.
Would it be in the parentheses, 10 plus 42 times 9 equals x plus 13 times 13?
Very good. You guys agree? Okay. And then we have to clean it up. And like Emily was just asking, if we want to, we can add these together. We could also distribute it. But I see 52 times 10 is easier. And this would be 13x plus 169. So 520 equals 13x plus 169. Subtract 169, I get 351 equals 13x. X is 27. Am I done?
No.
Good. What else?
The 13 to the x for no.
Yeah, NL is supposed to be whatever that value is plus 13. In this case, it's 27. So NL is 40. How are we feeling? 5, totally doable. 3, with some practice, it'll be doable. 1, this is undoable. Okay, great. Question? Say again? I still can't hear you. Yeah, go for it. I'm sorry to interrupt you in the middle of your work, but I'd like to take you to the next piece and then just give you the rest of the period to finish off whatever you need to do. So let's go to page 3, please. And surely you guys have worked with linear equations a lot. And you know that if I give you something like y is equal to 2x minus 3, that what that represents is all the possible points that could be plotted on a graph adhering to that rule. Right? I could make an x and a y table. And if I put in 0 for x, 2 times 0 is 0 minus 3 is -3. So I can plot the point 0, -3. If I put in the point 1, 2 times 1 is 2 minus 3 is -1. The point 1, -1 would also be on this. And I could choose crazy decimals, right? 0.379, and there would be some equivalent value for y that matches so that when I put in the 0.379, it takes me to that point in the graph. So today what we're going to be talking about is what a graph means to graph a circle, or what the equation would have to be to graph a circle. such that when I give you an X value and you plug it in, it'll tell you the Y value. And in this case, it might be two Y values. So what's important about a circle? What are the critical elements of a circle? Beautiful. That was our definition of a circle, which said that it has a radius, so that all of the radii coming out of this center point are all the same. So the two critical values there are the center, which I'm going to label as HK, and some point on the circle, which I'll label as XY. And what's so critical is that this radius is consistent. It's always R. Believe it or not, from just that drawing, I'm going to derive the equation of a circle. What I'm going to do is I'm going to turn it into a right triangle. We might have called these slope triangles back in the day. But the idea is, like, pretend that this one were at 12 and this one were at 9. How long is this leg of the triangle? It's 3, right? You just say 12 minus 9, that would find you how long this chunk is. So if this one is finishing at X and this one is at H, we can say that this length is X minus H. And we can do the same thing with this part up here. It's finishing at Y and it's starting at K, so this is Y minus K. And now I've got a right triangle with all 3 legs in terms of my variables. So I'm just going to do the Pythagorean theorem. X minus H quantity squared plus Y minus K quantity squared equals R squared. Believe it or not, that's our formula. Let's show how it works in the notes. So let's copy that here into the notes here. If you have colors, I recommend that we keep these components separate because they're relevant. So the X minus blank squared plus Y minus blank squared equals blank squared. And again, I'm adding in the H and the K there. And the R there. It is yours. Yeah, that's what I gave to you. And in this equation, what we'll see is that H comma K is the center of the circle, and R is the radius. So if H and K are the center, it's what's being subtracted from X and what's being subtracted from Y. So when I look at this example, what's being subtracted from Y? 2. So I know that down here in the bottom where it says the center and the radius, I know that the Y value is that 2 that's being subtracted. It's a little tricky. What's being subtracted from X? Good, -4. So the center of this particular circle is -4, comma 2. And what's the radius? It would be the square root of whatever's expressed there. So the square root of 25, which would be 5. With those bits of information, I should be able to plot this. My center is -4, 2. 1, 2, 3, 4, up 2. So that's my center. 4 to the left, 2 up. And now I need to find a circle that's exactly 5 units around. Well, I can count 4 spots that are 5 units away really easily. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, oops, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Once I've sketched those 4 extreme points on the edges, I should be able to just hand sketch the arcs to make it look like a circle. And yes, it's a humbling experience hand sketching a circle like this. It might come out looking more like a diamond. Okay, would you take a look at number 2 here? Let's see what we do for that. What's the center? Seven. That part's pretty straightforward. What's being subtracted from y? 0. And what's the radius?
4 or 2.
Good. Square root of 4, which is 2. So 1, 2, 3, 4, 5, 6, 7. And then go 2 in each of the 4 directions. Okay, flip to the second page, the next page after this, please. And in that top box, write the same equation again. It's exactly the same thing. Really dig it into your brain as you're doing it. It's the second time you're writing it. Think about from that what the center is and what the radius is. Okay, so HK is the center and R is the radius. So what if I give you the center and the radius? Could you write the equation?
Yes.
Sure. X minus 5 squared plus y minus 3 squared equals 2 squared. And you can leave it like that with the 2 squared, which looks so much like the formula. It's a little bit easier. Or you could choose to expand it out and call it a 4. Please do number 2. Yeah, sure. Okay. So this is an opportunity for differentiated effort here. If for the rest of this page, it's going to be exactly this kind of stuff. It's going to say, find the equation of the circle. And as you work your way down, it's going to give you little twists. Here, it gives you the diameter. How's that going to change things? You do half of that, and that's the radius. Here, it's going to give you square roots, but don't worry about it, because when you square it, they go away anyway. Here, it's giving you the circumference. So you'd have to remember that if the circumference is 2 pi r, that 6 pi is then 2 pi r, so 3 is r. In other words, you'll have to solve for r before you can then plug it in to find the equation. X plus 1 squared plus y minus 4 squared equals, radius is 3, so that'd be 9. So the rest of this page is the rest of your homework. You are responsible for pages 1 through 4. However, there is a page 5. I've labeled it the Algebra Challenge page because some of you are going on to Advanced Algebra Honors. Some of you are going on to Advanced Algebra, and you need to have strong algebra to get there. So what you'll find is this is completing the square, and I'll walk you through this in just a moment. These are asking you to do even more challenging ones using the distance formula and the midpoint formula to write the equation of a circle. So everybody, let's fill in these formulas just to get them in a nice comfortable spot for us. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And remember, these little numbers down in the bottom refer to the fact that this is one x value. This is a different x value. They're of different points. And the x's for 1 and the y's for 1 should match. Doesn't really matter which one is first. We've also got a midpoint formula, which suggests that we're getting a coordinate at the end that's the average of the x values for the x and the average of the y values for the y. If algebra is your kryptonite and you're planning to take on an intermediate algebra next year instead of advanced algebra, you can kind of tune out now and do the rest of the homework while I explain completing the square to the people who want to see it. Yeah. Okay, can I do that for you in just a second? Okay. All right, I can't have you guys talking during this though. Ladies and gentlemen, I cannot have you talking. Luke, what are you doing? Okay, I'm still teaching though, so I need you guys to please be quiet. If you want to quietly work on your work, you can. So traditionally, when we write out an algebraic expression, we put variables in front that are the constants, like ax squared plus by squared plus cx plus dy plus e equals 0. That's just a generic form of a quadratic expression in two variables. Girls, please just give me like 5 minutes, and then you'll be all on your own. So what we're going to try to do is turn this structure into a circle equation. When you get to pre-calculus and advanced algebra, you'll be given expressions like this, equations like this, and there are subtle differences that make it so it might be a circle, it might be an ellipse, it might be a hyperbola, it might be a parabola, all of the conic sections. So this is just an exposure of what it could look like as the process of determining that. Step 1 is to group the x terms together. So I'm going to take the x squared minus 2x, and then I'm going to group the y terms together, plus y squared plus 6y, and I'm going to take that constant and move it over to the other side. Just reorganized it a little bit. Now, this is the part where people get into some trouble. What we're trying to do is express the x thing as a perfect square and express the y thing as a perfect square. And we'll end up having a number here that'll be the radius squared. But in order for this to be a perfect square, there's a very special setup for it. And you might remember this from, for example, if we have x plus 5 squared, that really means x plus 5 times x plus 5. I get x squared plus 1 5x plus another 5x plus 25, which make x squared plus 10x plus 25. And if I do this with a number of different components, what I discover is there's a pattern. If it's x minus 3 squared, it's x squared minus 6x, double that, plus 9. If I do x plus 4 squared, it's x squared plus 8x plus 16. If I do x minus 10 squared, it's going to be x squared, what goes here? Minus 20x plus 100. Good. So there is a pattern to these, and we're using that pattern here in completing a square. If I want this first part to be a perfect square, what I'm going to have is x squared minus 2x. And then since this is supposed to be double, I'm going to cut this in half, minus 1, and then square it. So I'm going to say plus 1 right there. And since I've added a plus 1 to this side of the equation, I'm also going to add a plus 1 to the other side of the equation to keep it balanced. And then for the y, I'm going to do the same thing. I've got y squared plus 6y. Since this is supposed to be double, I'll cut that in half, which is 3, and then square it to make the last part, which is plus 9. And if I add that to the left side, I also add it to the right side. This whole 3-term trinomial expression now can be rewritten as x minus 1 quantity squared. And this trinomial, since this is double and this is the square root of it, can be written as y plus 3 quantity squared. And over here, I used to have a 6. I added 1 to make a 7. I added 9 to make a 16. So I'm stuck with a 16 on this side. But that gets it into a circle form. So what's my center? Good. And what's my radius? Square root of 16 or 4. Okay, so once again, this page is like a challenge page. It's great for you if you're planning to take on higher levels of math. You want advanced algebra and honors next year, you should do this. But everybody's doing page 1 through 4. Pages 1 through 4 are your homework for today. Submit them in Canvas when you're done. You've got the rest of the period to work on it.